Hello and welcome to the AI Research Roundup. I am Alex, and today is May 11th, 2025. We are looking at Scenethesis, a language and vision agentic framework for 3D scene generation, from Hugging Face's trending list, published just 6 days ago. This paper introduces an agentic framework, a system of AI agents collaborating to create interactive 3D scenes from text. It uses large language models, or LLMs, AI trained on huge amounts of text for initial planning, then vision perception. AI's way of understanding images refines layouts. An optimization module then ensures physical plausibility, so objects are placed correctly and act realistically. Alright, so this first figure really gives us a visual taste of what Scenethesis can do. We are looking at 4 distinct 3D scenes generated by the system from text prompts, like a peaceful beach during sunset, a spacious warehouse, a cute piano room, and a warm hospital ward. These visuals showcase the framework's success in creating diverse and detailed environments, both indoors and outdoors, which is a core aim. The system's ability to ensure these scenes are not just pretty, but also physically plausible, relies on sophisticated methods like signed distance fields, or SDFs. Signed distance fields are mathematical representations of shapes that help the AI accurately determine if objects are colliding. Now, building on that idea of using signed distance fields for accuracy, this next figure, figure 2, shows us what can go wrong when that kind of detailed spatial understanding is missing. We see 2 examples here, a relaxed bar lounge with chairs and a wine cellar with red wall bricks. These scenes, generated by an older large language model-based method, clearly have issues, like misplaced objects and just awkward spatial arrangements. This really highlights the challenge. Scenethesis addresses by adding crucial vision perception and physics-aware optimization to avoid these unrealistic outcomes. Okay, so this figure, figure 3, really lays out the Scenethesis framework's multi-stage pipeline. It all begins with a user prompt, say a peaceful beach during sunset. First, the large language model module does initial coarse scene planning. Then, the vision module refines the layout using a vision language model, or VLM, an AI that understands both images and text to create a scene graph alongside tools like Grounded SAM for pinpointing objects from text and Depth Pro for estimating 3D depth. The optimization module then ensures physical plausibility using semantic correspondence matching, aligning object parts accurately, and those signed distance fields. Finally, another vision language model acts as a judge, verifying spatial coherence. Okay, so after seeing how the Scenethesis framework operates, this table, Table 1, really gives us the hard numbers. It compares Scenethesis, which is labeled hours, against other established methods. First, for text-image alignment, it uses metrics like CLIP, that is, Contrastive Language Image Pre-training, BLAP, another text-image comparison tool, and visual question answering, or VQA. These scores essentially measure how well the generated 3D scene actually matches the original text prompt. And Scenethesis clearly leads here. The table also shows visual quality preference, where both AI and humans consistently preferred Scenethesis for aspects like object diversity and overall realism. Following those text alignment and visual quality scores, this next table, Table 2, shifts our focus to physical plausibility and interactivity. It shows metrics like object collision rate, or COLO, which tells us how often individual objects improperly overlap, and scene collision rate, or COLS, for the whole scene. We also see object instability, or INSTO, and scene instability, or INST-S, indicating if objects would topple over. For all these, lower percentages are better, and Scenethesis, labeled hours, has the best scores. For instance, just 0.8% for object collision rate. It also scores very high on interactivity, like reachability and walkability. Alright, building on those strong scores for physical realism, this next figure, figure 9, gives us a great visual of how different constraints refine the scene. It starts with an image guidance, which is the visual plan. Then, B, we see a raw layout. Step C adds pose alignment, which adjusts object positions for better fit, though not yet physically perfect. Next, D. The collision constraint prevents objects from passing through each other, but they might still float. Finally, E. The stability constraint makes sure everything is grounded and will not topple over, showing the complete, stable scene. So, as we have seen through those constraints, Scenethesis really brings it all together. The key takeaway is its innovative, quote, agentic framework, essentially a system where different AI components act as specialized agents, collaborating to achieve a complex goal. In this case, generating realistic 3D scenes. By cleverly combining language understanding, visual perception, and physics-aware optimization, it produces diverse, interactive scenes that are not just visually appealing, but also physically sound. This makes it super valuable for virtual content creation, and even for research in embodied AI, which is about creating AIs that can interact with complex environments, much like humans do. That is all for this edition of the AI Research Roundup. Thanks for tuning in.